As you can notice from previous example that to answer the question that some set of vector functions is linearly independent, we looked at this particular determinant. And what is this particular determinant is? If we denote our vector functions by, let's say, x1 of t, x2 of t, and x3 of t, then this determinant is exactly the determinant of the matrix where the first column is x1 of 0, the second column is x2 of 0, and the third column is x3 of 0. And this determinant has a special name. The name of it is Wronskian. So let me give the precise definition what Wronskian is. So if x1, x2, and so on, xn is a set of vector functions such that the coordinates, let's say xj of n, are x1j, x2j, and so on, xnj, then the Wronskian of this x1 and so on, xn, at a point t is the determinant of the matrix which consists of this vector function. So the first column will be the first vector function and so on. So this will be x11 of t, so the first xn1 of t, x12 of t, and so on, x1 and 1 and 2 of t, and so on, x1n of t, and so on, x and n of t. Okay, so what we did in previous example, we proved that to prove that something is linearly independent, we proved that Wronskian of x1, x2, and x3 at a point 0 is non-zero, right? And from this we conclude that the set x1, x2, and x3, this is a set of linearly independent functions. And in fact, in general, the following result, let's call it theorem, if x1 and so on, xn, is a set of solutions of some homogeneous system, x prime is ax, then the fact that these are linearly independent is equivalent to the fact that the Wronskian of this x1 and so on, xn, at some point t0 is non-zero. So, if we have some set of solutions of some system, then to prove that the set is linearly independent, we just calculate the Wronskian and find one particular point from the interval where we study this question, where the Wronskian is non-zero. If we can do this, then we can conclude that the set is linearly independent. If we look now at this theorem, you maybe have a question: is this condition that x1, x2, and so on xn must be a set of solutions of some homogeneous system, is it really necessary to have in this theorem? Maybe some arbitrary set is linearly independent if and only if the Wronskian is non-zero. In fact, there is a proposition which can be proved if x1 and so on xn some arbitrary set of vector functions such that the Wronskian xn is non-zero at some point, then you can conclude that this set is linearly independent. So one implication from here to here is in fact correct. But in this case, if this set is arbitrary set, the backward application is wrong. The fact that x1 and so on xn is linearly independent in general does not imply that Wronskian is non-zero at some point. So the backward implication of this theorem fails to be true without this condition here. And let me show you this on an example. So assume that we have a set of these three vector functions, x1, x2, and x3. Let's firstly show that these three vector functions are linearly independent. To do this, we assume first that these three are linearly dependent. It means that there are C1, C2, C3, which are not all zeros, such that C1, 1, 0, 1, plus C2, T, 0, T, plus C3, T square, 0, T square, is 0 for any T, right? This means linearly dependent. And if we just calculate the first row of this, we get C1 plus C2T plus C3T squared is 0 for any T. For example, if we take T to be equal T to be equal 0, so take T is 0, we get C1 is 0. Take T is, let's say, 1, we get C2 plus C3 is 0. Take T is minus 1, we get minus C2 plus C3 is 0, which means that C2 is C3 is 0. So you see that we get the contradiction. We assume that these are not all zeros, but we get that all of them are zeros. So it means that the set is linearly independent. Okay, the set is linearly dependent, but the Wronskian, if we calculate the Wronskian of x1, x2, x3 at any point, this will be the determinant 1, 0, 1, t, 0, t, t square, 0, t square. And this will be 0, of course, because one line of this determinant is zeros, right? So you see that the Wronskian is, so the fact that these are linearly independent doesn't mean that there is t0 where the Wronskian is non-zero. So we get the example which is linearly independent set, but the Wronskian is 0 for any t. Okay, so what is wrong with these three vectors? What is wrong with these three vectors? These three vectors, the vectors x1, 1, 0, 1, x2, t, 0, t, and x3, t square, 0, t square, are not solution of any system like this. This is not possible to find a system for which these three vectors are solutions. Okay, let's prove this. Assume that x1, x2, and x3 are solutions of the system, let's say, of the system with A, since the vector is of dimension 3, so A must be 3 times 3 matrix, so A11, A12, A13, A21, A22, A23, A31, A32, A33. So what does it mean? It means that x1 satisfy the system, right? So if we substitute x1, what do we get? The derivative of 1 is zeros, right? So we get 0 vector here. The matrix is A11, A12, A13, A21, A22, A23, and A31, A32, A33 times the vector, which is 1, 0, 1. So from this we can conclude that, for example, A11 plus A13 is 0. This is just will be enough for me, okay? A11 plus A13. So when we multiply the first row times this vector, we must get 0. So this is 0. What if we sub in x2? So the derivative of x2 is 1, 0, 1. And what do we have here? That the same matrix times t, 0, t. So from this, if we multiply the first row, 1, A11, A12, A13 times this one, we get t, A11 plus t, A13 must be 1, right? So 1 here. If we take this t out of the brackets, is 1. And this is impossible because we already proved that this is 0. So this is 0. So this thing is impossible. This thing is impossible. So these three vectors cannot be solution of any system.